Last week, we looked at some of the factors that influence the Earth's climate and then the techniques that geologists and climatologists use for reconstructing ancient climates. And today we're going to look at a few complicating issues and then follow the Earth's climate through geologic time and finish with looking at our current climate, how it compares with those of the past, and what the ancient climates can tell us about our future on this planet. So complicating factors, probably one of the biggest ones when you go to ancient climate, is the incompleteness of the geologic record. Erosion is the eraser of geologic history. If you were to fly over part of Utah 120 million years ago, you would have seen a shoreline, a coast, a seacoast. And in those forests off to the left, there would be lots of dinosaurs and a shoreline that advanced and retreated. And we can see those shorelines today in these rocks that are the bright colored sort of ledges that you see in the upper part of that cliff. This is the Book Cliffs in Utah. And at one time, those rocks extended way out to the right, a long way, and they've just been eroded back. And that erosion will continue. Eventually, those rocks will be gone, and that part of geologic history will be lost forever. But there's another way to lose geologic information, and that is when you get a collision of continental crust, because the colliding plates generate immense heat and pressure that changes the rocks completely. For example, fossiliferous limestone can end up as a marble, in which you can see basically nothing but the fact that it's made of calcium carbonate. Similarly, you can have a fossiliferous shale with all sorts of bedding features. It's converted to a mica schist, which contains none of that information. Much of Canada is underlain by some really old rocks, older than 1 billion years. And a lot of them look like this. And it's impossible to tell when you look at a rock like this, whether it started off even as a sedimentary rock or some kind of an igneous rock. It's been completely changed and all that initial information is gone. Then there's the issue of age and the fact that the gaps in the record increase as we go back through time. You can sort of see that in this representation here of ages. This is looking at sort of the basal geologic time intervals that are recognized for different periods of time. In the last 2 million years, there's 7 time intervals that are recognized. In the preceding 65 million years, there are 24. In the 475 million years before that, there are 78. And then we go back to the 2 billion years before that, there are 10. And in the first 2 billion years of Earth's history, there are only 5 recognized time intervals. Part of this is due to the fact that through that early part of the Earth's history, there are no multicelled organisms, there are no fossils. So the only way that we can date rocks is using radiometric dating, which works on igneous rocks and not on sedimentary rocks, but all of the information about the environment is recorded in the sedimentary rocks. So basically, we have a big gap in our age. Plate tectonics is another complicating factor. In Ohio, there are rocks, Devonian, which is their age, 400 million year old rocks that exist, that accumulated in a subtropical environment. And back when I went to school, it was considered that the Earth was very warm 400 million years ago. But plate tectonics shows us that that particular part of the Earth 400 million years ago was just south of an equator. It was a subtropical environment. So, and also one sample doesn't give you a global perspective. You need a lot of samples that are appropriately distributed. And that's the only way that you can really put together a global climate assessment. So plate tectonics, we have a pretty good idea of where how the continents were aligned back to about 600 million years ago. But as we go back further in time beyond that, it is pretty much guesswork. So that's another factor that limits us. So overall, I would say that our understanding of ancient climate declines markedly with age, and as we get back beyond about 500 million years, it's pretty sparse with a couple of exceptions that I'll talk about in just a few minutes. So let's look at the Earth's climate through geologic time. And what we're going to be looking at is a combination of what the climate was and how it shaped the evolution of life on the planet, which in turn partly shaped the climate. So there's a connection between evolution and climate. So long, long ago in a galaxy not that far away, about 5 billion years ago or so, a giant star exploded. It produced a nebula, a huge cloud of interstellar gas and dust. And within that cloud, material was collecting around a newly formed star. Around 4.6 to 4.7 billion years ago, that star would become our sun. And the debris that was orbiting around that newly forming star started to agglomerate, collect by the process of gravitation into bigger and bigger chunks. And eventually, about 4.6 billion years ago, we have the origins of the planet Earth. The oldest known rocks, and you can see there's a fairly widespread range of dates assigned to those rocks, occur in Canada, and they're around 4 billion years old. The period before 4 billion years is described as the Hadean, and it was pretty hellish. Lots of bombardment, and the Earth was extremely hot. And somewhere during that period of time, during the Hadean, an immense event happened because we think the Earth got struck by another small planet, maybe a little bit smaller than Mars, collided with the Earth and knocked a huge amount of the Earth out into space where it orbited around and eventually formed the moon. NASA has proposed that after that collision, the atmosphere of the Earth was about 3,600 degrees Fahrenheit, which is, as far as I know, sort of the earliest indication of an Earth climate, a very, very inhospitable climate. That impact did a couple of things that did affect our climate significantly. One, it probably is responsible for the rotation of the Earth on its 24-hour round trip. And had that not happened, the Earth might have had one side facing the sun under unrelenting sunlight and the other side in eternal dark. And the only place where anything could live would be sort of in the shadow zone between the two, a very, very different kind of Earth, and probably one with a very, very different biological history. It also knocked the Earth's axis into a tilt compared to the plane of rotation around the sun. And that tilt is responsible for our seasons. So our seasonality may have originated with that impact as well. So 4 billion years ago, the Earth might have looked something like this. The moon was much closer at that time. The sun wasn't as bright because, as we noted last week, the solar luminosity, the brightness of the sun, has increased through time, and it was only at 4 billion years ago about 70% of its brightness today. And so this was the nature of the Earth around 4 billion years ago. very inhospitable place, um, strange atmosphere. And as long as the Earth surface was hot, water couldn't accumulate on it. But it cooled about 3.8 billion years ago to the point where liquid water could accumulate. My guess is it rained and rained and rained and rained and rained some more and then rained some more. And puddles became ponds, ponds became lakes, lakes became seas. And somewhere in that period of time, active plate tectonics probably originated. And in plate tectonics, mantle material wells up from ridges that now lie in the ocean and spreads out as a thin, dense volcanic crust, oceanic crust. And that spreads, moves until it runs into a continent. And the continents are made of material that's lighter, it's more buoyant, it's like a cork. And so the dense crustal plate of the ocean slides underneath the continental plate. And this provides us then with a potential for ocean basins between the continents. And so it may well be that somewhere back around 3 to 3.5 billion years ago, we have the first ocean basins and the first oceans. The atmosphere is really not very hospitable, no oxygen, a lot of methane, carbon dioxide, nitrogen, greenhouse gases. It probably was quite warm. And around the margins of the seas, 2.5 to 3 billion years ago, some strange structures were forming, biscuit-like structures, that left a record in the rocks that looks something like this. These are called stromatolites. They're very, very common in these older, much older rocks, the sedimentary rocks. And no one knew what they were until the 1950s, when they were found in a saline bay off the coast of Australia, Sharks Bay. And these are preserved there because the water is too salty for organisms to live that would eat them, which would happen on other coasts. So we now have photosynthesis. Photosynthesis is a process that takes carbon dioxide and water, and using the energy of sunlight, creates a sugar molecule, essentially food, and oxygen. And so we take 6 carbon dioxide molecules in, and we release 6 oxygen molecules. The result is that atmospheric carbon dioxide goes down and oxygen goes up. And so about 2.5 or so to 2.2 billion years ago, oxygen is replacing atmospheric carbon dioxide. And this has a big impact on the climate because carbon dioxide is a greenhouse gas and was instrumental in keeping the Earth warm. And so what we find in rocks of that age are things like this dropstone on the left or this tillite on the right, both produced by glaciation. And so back during that period, from about 2.2 to 2.4 billion years ago, there was large-scale glaciation on the surface of the planet. A very cold time in the Earth's history, and maybe the first snowball Earth, where much of the Earth was covered by ice. This event is followed by what I think is one of the most intriguing parts of the geologic time zone. And that is, it's called the boring billion, but it's essentially a billion, or actually more than a billion years, in which virtually nothing happens. It's an unchanging world. There are changes in the nucleus of the single-celled organisms that pave the way for changes later on. But basically, they all stay pretty much the same. There's a billion plus years that there's no particular change. For this reason, I think if we ever find life on another planet, it's probably going to be something like this. But that ends about 600 to 700 million years ago with a second episode of glaciation, what is referred to as Snowball Earth. And it was a really cold time. One estimate of the average global temperature was 37 degrees below 0 Fahrenheit. I've been in 40 below, and that's really cold. And to think that the average global temperature could be in that range is staggering. The continents were amassed over the South Pole at the time, which was probably a contributing factor to that glaciation. And there's some question as to whether it was a total freeze over, a snowball Earth, or a slush ball Earth, in which it was mostly snowball, but there was a large patch of water in between. Somehow the organisms survived, either in this open waterway or around volcanic areas where the water would have been kept somewhat warmer. But life did survive this event. But the rocks are really amazing in one respect, and that is what we have here at A is a rock that's layered. It's a type of limestone, basically, and it sits on top of a rock that is essentially a glacial till. And that limestone at the top has estimates that it represents a global temperature of more than 90 degrees Fahrenheit, and it sits directly on ice age deposits. And this is really a strange situation. It is, whoops, let me go back to this. One of the hypotheses is that if the Earth is pretty much covered with ice, there's no weathering. Carbon dioxide, which would normally be consumed in the atmosphere by the process of weathering of rocks and removed from the atmosphere, continued to build up, and it built up to the point where the greenhouse effect kicked in, and so there was a sudden change in the climate. But this is still remains a real mystery. And in its aftermath, we get evidence of the first multicellular organisms. These are strange things. They're imprints in the rocks. They're found all over in the world in rocks, marine rocks of this particular age period. And we haven't a clue what they were. Some of them may have been jellies, some of them may have been sponges. I suspect that many, if not all of them, were effectively colonies of cells that had come together and were working as a community. Sponges are we think of them as an organism, but you can take a sponge, put it in a blender, run the water through the blender through a sieve, and put it in, let it sit, and in just a few days, it'll reconstitute itself into a sponge. That to me is a colony, not an individual animal. But whatever it was, it set the stage for an explosion of diversity. Suddenly, we have, starting about 543 million years ago, we have an explosion of life forms. We have most of the phyla the major phyla that we know today, the big building blocks of biological classification, and the classes, which are another group of biological groupings, you can see just grew dramatically during this early period of the Earth's history. Lots of ideas about why that happened, but probably the most cogent is that the oxygen levels increased to a critical point. This is an estimate of oxygenation of the atmosphere through time. You can see the effect of photosynthesis at about 2 billion years. And then about 1 billion years ago, the oxygen started to increase and then really went up rapidly. And it was at that beginning of oxygenation that we have this abundance of new life forms. My guess is that what happens is that oxygen, the increased oxygen, allowed for mobility. For the first time, animals could move. There are no tracks or trails in the rocks prior to this explosion. And there are abundant tracks and trails afterwards. So mobility is one of the things that happen. Well, mobility can allow for predation, and predation can produce an arms race, basically, where an animal develops teeth, so another animal gets a better shell. Its prey gets a stronger shell, which means the other animal has to adapt if it's going to continue to eat and survive. So lots of changes, very rapid evolution at that time. The animals in the Cambrian seas were pretty weird. Lots of things that we would not see in our current ocean. And that introduces us to the Paleozoic Era. And it consists of 6 geological periods. We'll go through these. But the Paleozoic was a time of real change on the surface of the Earth. Starting off, it went from a lifeless landscape. And I know this is lifeless because it's a picture from Mars. I think it's lifeless. And within a few 100 million years, we have a change to great lush forests. We start with things like jellies, and we end up with large sailback complex predators. So lots of change during the Paleozoic. And the continents moved around as well. Starting at the top left, we go through a transition. You can see the continents shifting from moving to the South Pole and then accumulating and forming, and they form and unform supercontinents as they go. So lots of change. We're going to look at the geological periods of the Paleozoic era in turn. And one of the things we're going to focus on is extinction events, because extinction events are representing major changes of some kind in the environment. And climate is the most likely candidate for most of those changes. So we start with the Cambrian. The Cambrian is probably cool at the first. It's still the lingering after effects of Snowball Earth, but it warms up, and it's generally considered to be fairly warm and temperate. The continents were arrayed something like this. There don't appear to be any glaciers that formed during that particular time, so it was probably warmer than it is today. The rocks are kind of weird. My specialty as a geologist was in the interpretation and study of shallow marine sandstones. And I've seen the Cambrian sandstones, and they've always looked really weird. They have strange minerals. Glauconite is a mineral that you just don't see that often in shallow marine sandstones and rocks that are younger than the Cambrian. I don't understand this, but there's something in the water chemistry, I think, that was different in the Cambrian period. There were 3 extinctions during the Cambrian. The latter one, the latest one, is linked to flood basalts in Australia. And if you remember from last week, flood basalts are long periods of volcanic eruption that really can change the climate. The others, not real clear, but some studies done this last year on rocks in Siberia indicate that the oxygen was fluctuating kind of wildly during the latter part of the Cambrian. And nobody knows quite why that would happen, but it would wipe out a group of organisms, then come back and a whole new group would evolve to replace them. So this is considered a possible reason for that very rapid evolution that occurred during the Cambrian, linked to these fluctuations of oxygen in the water, and we really don't know why those fluctuations happened. We move on to the Ordovician. The Ordovician follows from the Cambrian. The Ordovician starts to get cold, especially towards the end. Glaciers form. It's one of the cold periods in the Earth's climate. And there is a significant extinction event that relates probably to those cold climates and glaciation. The Silurian is the shortest period of the Paleozoic. Some think it shouldn't be a period at all, but one of the things that happened in the Silurian that was really important is that plants moved from the water onto the land for the first time. They developed the capability to survive without being submerged. And so this is a start of something that's going to really change the Earth significantly. The continents were arrayed something like this. There were continents at the South Pole, but there's scant evidence for any glaciation during this period of time, which suggests that getting glaciation is not just a matter of having continents over the South Pole. And we know that from what we see in the most recent part of the geologic history that I'll get to later. The Silurian has one event of extinction that is not particularly well understood. And we move on to the Devonian. Devonian is an interesting time. The continents are starting to amass, collect together. The Devonian is not a time of glacial activity, but it is when the first trees evolve and indeed the first forests. But the Devonian is known as the age of fish because fish really grew. The first sharks appeared during this period of time. Many, many fish in the ocean, and probably enough big predators that one of the ways to survive was to get yourself out of the water. And so we have, during the Devonian, the first animals that come out on shore, large tetrapods, amphibians basically, that crawled out of the water and were still linked to it because they had leave their eggs there, but they themselves are air-breathing and first land animals. The Devonian has a number of extinctions, and it is roundly debated as to what caused them. Really, we don't know why those extinctions occurred. The following period is the Carboniferous, and the Carboniferous is an amazing time. It has huge ramifications for our modern world. Our history is tied up in the Carboniferous, and it is so important that I'm going to be giving a talk on it by itself in a few weeks. But the Carboniferous is a time of great rainforest, lots and lots of trees, and those things that are flying in the air are not birds. Those are insects. This is a time when the insects got up to maybe wingspans of nearly 2 feet. There were some other pretty nasty, amazing, creepy crawlers at that time as well, that I'll talk more about later on in the other talk. The Carboniferous is also unique because it has the highest oxygen content, atmospheric oxygen content of any time on the Earth, up to estimates of nearly 35% of the atmosphere was oxygen, compared with the almost 20%, 21% that we have today. Why was the oxygen level that high? Well, there was one thing that was missing during the Carboniferous period, and that was fauna, animals. There were animals creeping out, as I said, the amphibians, but basically nothing like the array of animals that we have today. And all of us animals, all of us, consume oxygen. We're oxygen consumers, and we don't put it back. And so we take oxygen out of the atmosphere. And so there were not that many animals during the Carboniferous. My guess is that there weren't enough animals to draw down the oxygen that was being released by all that photosynthesis during the Carboniferous. There were a couple of extinctions, one of which, the biggest of which, seems roundly ignored in the literature, and the focus is on the rainforest collapse, because that was a major change in the character of the flora of the time, because the rainforest largely disappeared, and that was probably a climatic event, a drying out. And it took us to the Permian, the final period of the Paleozoic. The Permian, the continents were all arrayed. It was cold. There was glaciation at the outset. There were lots of large reptiles that existed. This particular reptile has a skull type that is reflected in all the mammals today. This is probably in the line of development of the mammals. There are two extinctions, one of which is linked to a flood basalt in China that changed the climate drastically, but the other one is also connected to flood basalt in what are called today the Siberian traps. This is a large area that erupted back about 250 million years ago, and the eruption was through a Carboniferous coal field. There was a lot of coal that was burned by this eruption, and the burning of that coal pumped great amounts of carbon dioxide into the atmosphere. It probably looked something like this, and the result was an extinction, the greatest extinction that's really occurred in geologic time. It's called the Great Dying. 96% of the marine species are removed, and 70% of the land species. The loss of marine species suggests that acidification may have been an additional factor in the extinction due to all the excess carbon dioxide. Well, that ends the Paleozoic and ushers in the Mesozoic Era, which has three periods: Cretaceous, Jurassic, and Triassic. And this is the age of the dinosaurs. There are not that many extinctions during the Mesozoic. It's a pretty benign time. There's a big one at the end of the Triassic and another big one at the end of the Cretaceous. But otherwise, it seems to be a time of fairly stable climate. The Triassic, that begins it, the Earth was starting to form was in a new supercontinent, Pangaea, and it was probably pretty warm over much of this time. The forests were covered by conifers, pine-like trees, ginkgos, and the animals that ruled were large lizards called archosaurs. And there was during this time that the first dinosaurs appeared around 230 million years ago. And if you notice, there's a strange little creature down in the lower left of this picture. This is a Cenodon. It's a reptile. It's got whiskers, at least in this representation. And the Cenodonts, by the end of the Triassic, will produce the first mammals. And the Triassic ends with a bang. Again, flood basalts. This time where the supercontinent Pangaea starts to pull apart. And there's rifts with volcanics going on within those rifts, pumping out great quantities of lava. You see the outlines of the continents of today shown here. And as they moved apart, they carried those ancient volcanic deposits with them. It was a big event. Again, clouding the earth and ending the rule of the Archosaurs. But the dinosaurs survived, as did the mammals. And we enter the Jurassic, undoubtedly the best known of all the geological periods because of the book and movies. It was a very clement time. The dinosaurs ruled the earth. The continent may have looked something like this, and there have been attempts to establish the climate regions, climate zones. Notice we've got an arid zone in the center, sort of the equatorial areas, and if we look right there, that is where this photograph came from. If you remember last week, we were talking about dune deposits indicating arid conditions, and these are the dune deposits from Utah that formed during that period of time. The Jurassic may end with an extinction, although there's some debate about how significant that extinction really was. But there does seem to be a change from a rather arid, semi-arid conditions, more humid conditions of the Cretaceous. But the Cretaceous got pretty warm. Equatorial Atlantic water was 15 to 17 degrees Fahrenheit warmer than it is at present, which is really warm. But overall, it was a great time to be a dinosaur until the very end, 65 million years ago. A couple of things happened. In what today is India, the Deccan Plateau, there was a volcanic eruption, a set of flood basalts producing layer after layer. All these dark streaks are volcanic rocks that were produced in succession by the volcanic eruptions in this area. And they would be putting carbon dioxide and water vapor into the atmosphere, certainly making a potential for change. But something else happened as well. A rock about the size of Mount Everest was headed toward the Earth about 50 times faster than a bullet moves, and slammed into the Earth. And some estimates are that it released 200 to 500 billion tons of sulfur and 300 to 650 billion tons of carbon dioxide. So this could be a major game changer in the atmosphere. But there was another thing that happened, and that was that it vaporized a huge amount of rock that escaped back into space, where it coalesced and formed a cloud around the Earth, and then came raining back in the form of little pellets that are found all over the Earth at this time. And these pellets would radiate heat, and that could turn the Earth's atmosphere into an oven. It's estimated that the atmosphere could have gone up to 1200 degrees Fahrenheit for several hours. Really nasty weather. But the result is a barren landscape. The forests are gone. The Earth is changed. The only survivors seem to be animals that lived in holes, like mammals, birds, or laid their eggs beneath the surface, as do turtles and crocodiles. And that ushers in the Cenozoic Era, our current era. The Cenozoic, and you see we've had a time change here. We've changed our scale. We're now looking at tens of millions of years. And after that big extinction event at the end of the Cretaceous, There's only one real event that occurs during extinction event that occurs during the Cenozoic. We have a much better temperature record now. Again, it's this whole issue. The closer we get to the modern time, the more complete the record and the better the information. So now we have a climate curve that we can really start to focus on. Immediately after the Cretaceous, the temperature rises, and whether that is the result of the impact or the volcanism, I'm not sure. That might be an effect of the volcanism, because I don't think the impact effects would last that long, like 10 million years. Then we go into a very warm period, and there's a spike in there that's drawn a lot of attention. It's called the PETM, the Paleocene-Eocene Thermal Maximum. And temperature went up 5 to 9 degrees centigrade in a few thousand years. It's of particular interest to climatologists today because they think a similar thing might happen at the present time. What was the world like at the PETM? Well, there were no polar ice caps. If you look here, you note that most of the major cities of the world would be inundated because sea level stood particularly high. And places like the Canadian Arctic, the fossils indicate that it was a very clement climate. So it was really a very warm time in the Earth's history. There were some flood basalt eruptions that occurred around that time, but the most popular explanation right now for it is that it was methane escape, runaway methane escape. Remember, we talked about this last week, where there's a huge amount of methane frozen under the continental shelves. And as the Earth warms, that methane's released. It's a greenhouse gas, which makes it still warmer. And so you get into this runaway greenhouse effect caused by the methane. Whether that was it or not, we're still not really sure. But that is an interpretation that is often put toward that particular spike. Then the Eocene kind of gradually cooled until we get to about 34 million years ago. And there's a sudden plunge in the temperature that's coincident with the development of Antarctic glaciation. Why this sudden change in the climate? Was an extinction event. It's the only real extinction event in the Cenozoic. But what caused it? Well, it happens at a time when the India plate, which was almost a small continent itself, was coming north at a fairly rapid pace, moving towards the Eurasian plate. And at about that time, it collides, forming the Himalayas and putting lots of new fresh rock up the surface where it could be weathered, and perhaps a drawdown of carbon dioxide in the weathering zones. And so a decrease in carbon dioxide due to that collision is one of the things that's been proposed as a cause of that particular precipitous plunge in the temperature. But we don't know. That's one explanation, but it was a very dramatic time, a dramatic change, one the likes of which we really haven't seen that much otherwise. And we go through a long period of Antarctic glaciation that finally ends about 26 million years ago with those glaciers melting, and temperatures rise back up into the Miocene period. And the Miocene is recognized as one of the warmer times in recent past. It was a time of grasslands, when the first grasslands evolved. And in the middle of it, there is something called the mid-Miocene climate optimum. a spike in the temperatures that lasted, several million years. And this is coincident with the Columbia River basalts, a large flood basalt that occurred at that time, and it is completely coincident with that climate optimum. So maybe that was the cause of that climate change in the Middle Miocene. Then Antarctica reglaciates. Glaciation begins in Greenland, the temperatures start to fall, and we go into the recent ice ages. And here we change our time scale again. We now go back to look at the past 5 million years. And this is a time that last week we talked about the Milankovitch cycles, a change from the 41,000 year cycles to the 100,000 year cycles, a general decline in temperature as we get closer and closer to the modern. And we're going to change our scale again as we get closer to the modern. We're going to look at the past 6 million years, or 600,000 years, excuse me. And now we can start to see the glacial and interglacial episodes as indicated by Del 18, which we talked about last week as a geological thermometer. And so we have this alternation of glacial versus non-glacial over the past, close to 1 million years. And this is the Pleistocene Ice Age. At its maximum, glaciers covered about half of North America and a sizable amount of Eurasia, and water to produce all that ice came from the sea. Monterey Peninsula was not covered by glaciers. It was probably covered by big sand dunes because we see giant sand dunes all around the land areas. We go back inland. If you drive 68 through the strawberry fields, those rounded hills are all sand dunes that formed during the Pleistocene. Sea level went up and down as a function of the ice being trapped, removed from the ocean and put into the glaciers. So when the glaciers form, sea level drops, and then as the glaciers melt, sea level comes back up again. If they'd been here about 20,000 years ago, could have walked out a long way on what today is the Monterey Bay Shelf. It was all dry land, maybe lots of sand dunes, maybe some vegetation out there. A very, very different kind of world than it is today. And we are ourselves an ice age species. The earliest Homo sapiens occurred during one of the high stands, one of the warm periods, about 300,000 years ago. And we've survived all of those ups and downs ever since. In fact, they may well have shaped who we are. If we go to the last 100,000 years, we got still more detailed record, lots of fluctuations during the glaciation, and not sure why we have these changes. They may relate to some of the Milankovitch cycles. Then we're going to have to change our scale again and look at the last 20,000 years. And we look at the last 20,000 years, we see we started to come out of the glacial event and then drop back down into it in something called the Younger Dryas. And this plunge in temperatures, a return to glacial conditions when it looked like we were coming out of it, has been much debated. Some think that there were changes in the oceanic circulation that caused it. Others attribute it to volcanoes, sunspots, impacts. We really don't know why that dropped so precipitously, but it did. So what can the Earth's climates tell us about, what do the ancient climates tell us about the Earth's future? Well, we can look at this two ways. One is long-term, and over the long haul, climatologists look at the Earth as being in either greenhouse conditions or icehouse conditions. Greenhouse, it's warm, obviously. Icehouse is when we have the glacial episodes. There are fewer of those. Most of the time, the Earth is in a greenhouse environment. And so typically the Earth would be considered warmer than it is today. And eventually, it stands to reason that the Earth will go back to greenhouse conditions. And once again, it'll be quite a bit warmer than it is at the present time. And that is not anything to do with what we're doing to the climate right now. We may push it back to greenhouse conditions faster than it would otherwise happen. But we live very comfortably in the icehouse conditions. Short term, there's a lot of fun stuff to think about. Over tens of thousands of years, what might our climate do? Well, one of the things is stuff happens. The Younger Dryas, just the bottom dropped out of the temperature for reasons we still don't quite understand. Could it happen again? Whatever it was? Yeah, I presume it could. It would be pretty devastating. Yellowstone is a caldera. It is a giant volcanic crater, and it sits on top of a hotspot in the Earth's mantle, and the crust is moved across that hotspot. And as it's moved, the volcanic eruptions, the ancient volcanic eruptions moved with it. And the most recent of these are close to its present location, and the last one was 600,000 years ago. And that one spread ash over probably 2/3 of the United States. Some say that 2/3 of the United States would be uninhabitable if that happened again. So did it disrupt the climate pattern? Well, let's look at 600 years and see. And what we see at 600 years is the Earth was coming out of a glacial episode, and then it abruptly went back into a cold climate again. So maybe there was a major disruption of the climate due to that mega eruption. So major climate change can happen very rapidly in geologic terms. You see that with the temperature spike of the Eocene and Paleocene temperature rise. And you can see it again dramatically in the temperature rise at the end of the Younger Dryas. 16 degrees centigrade in 250 years, that is phenomenal. But it led to a period of climatic stability. And that period of climatic stability is when human civilization developed. It is very likely that had we not had that period of stability, it's likely that human civilization wouldn't be what it is today. So how imminent is the next ice age? We're at an interglacial. Presumably we will go back into a glacial period again. So how close are we to that? And can the past million years provide insights into the future? Well, one thing we can see is the current cycle is not different so far from any of those in the past. So we wouldn't expect it to change very much in the future. The current temperature is about that of the past interglacial maxima, and the interglacial peaks are short-lived. They last about 10,000 years or less. And it's been 10 to 15,000 years since that last interglacial rise peaked. So presumably we're due to go into a distinctly cooling phase. So is our warm interglacial period over? Well, a couple years ago, it was thought that we were right on the edge of a new ice age. And it was caused by the winter of 2018-19, particularly in the Midwest, which suffered from a really nasty cold snap. Some cities had temperatures were colder than parts of Antarctica. And it was caused, according to NOAA, the National Oceanographic and Atmospheric Administration, by masses of cold air. There's a polar vortex of cold air that swirls around the Arctic. And in the winter of 2018-19, masses of that cold air plunged toward the interior. But the reason they did that was that warm air disrupted the vortex, and the Arctic air that was disrupted moved south. So this was not the onset of an ice age. This was caused by climate disruption due to the current warming of the globe. So you can see, though, that there is a general decline in temperature over the last 5,000 years or so. And so are we experiencing the beginning of a temperature decline? Can that offset the rise in temperature that worries us today? And the answer is no, because the decline is so much, the rate of decline is so much lower than the rate of rise of the temperature that we observe that it doesn't really have an impact. And so it's not going to materially change our climate today. Well, what do the past 400,000 years tell us about the next ice age? Well, there's a very rapid transition from glacial to interglacial. It's on the order of 10 to 20,000 years from deep glacial to very warm interglacial. So it happens quickly. But it takes a slower return to go back into glacial conditions. Temperature drops, but we don't get into glacial conditions for probably 35 to 50,000 years to get us back into fully glacial conditions. So it's been 15,000 years since the rise, if we discount the Dryas event. And that means that we've probably got 20,000 to 35,000 years until we're back into a true glacial episode. And your outlook on that may depend on where you live. But there's no reason to think this pattern will not be repeated. That is the future, but it's a long way off. One of the things that I tried to find out this time around was, how does the current rise in temperature compare with those in the past? The rise in global temperature in 100 years from 1920 to 2020 is 1.2 degrees. And we can plot that 1.2 degrees on this diagram. Now, and that's what the arrow represents, 1.2 degrees rise. At this particular time scale, it would be essentially vertical. And I don't know how accurate those ups and downs are in the time from the present day out to 100,000 years, but if they are accurately represented, the change that we've seen in the last 100 years is not excessive and is not something that is dramatically different from the natural changes we've seen in the past. But if it went on for another 100 years, or the rate increased, it would definitely be out of the normal range that we have seen. So we live at a cool time on a planet that has endowed us with incredible natural resources. It's a very special place, and we need to take care of it.